This is a ball. I'm going to cut it into 5 pieces and then reassemble those exact same pieces into 2 balls, each one the exact same size as the one I started with. No stretching, no adding material, just rearranging. This isn't a trick, it's a real theorem, proven by real mathematicians, and for almost a century, it's broken people's brains. Because it means something we all assume about math is wrong. Welcome to one of the strangest results in all of mathematics, the Banach-Tarski Paradox. And by the end of this video, you'll understand exactly how 1 can become 2. Here's what most people assume. If you cut something into pieces, the total amount of stuff doesn't change. Cut an apple into 5 pieces, you still have 1 apple's worth of apple. That feels obvious. It feels like a law of the universe. In 1924, 2 mathematicians, Stefan Banach and Alfred Tarski, proved that this obvious law is false. Not false in some metaphorical sense, mathematically provably false for a perfect mathematical sphere. So either mathematicians are wrong, or reality is weirder than we think. Spoiler: it's neither, it's something stranger. To understand this, you need to forget how cutting works in real life. When you cut a pizza, you're cutting along smooth lines. Banach and Tarski didn't do that. They used a special kind of set theory to divide the sphere into pieces that aren't shapes at all. They're infinitely scattered clouds of points, chosen using something called the Axiom of choice. Here's the key trick. Each piece is built by picking individual points on the sphere's surface based on rotation sequences. Think of it like sorting every point on the ball into one of 5 buckets based on an infinite, never-repeating pattern of rotations. These pieces are so jagged, so infinitely complex, that they have no defined volume. Not zero volume, undefined. They're not solid chunks. They're more like infinitely fine dust, mathematically structured so that when you rotate and reposition them, they fit together into not 1, but 2 complete spheres. You're not creating new material. You're exploiting the fact that infinity doesn't behave the way our intuition expects. Now, you might think, this has to be some kind of loophole, a trick of definitions, and in a way, you're right. But it's a loophole baked into the foundations of modern mathematics itself. The axiom of choice is one of the basic building block assumptions nearly all of mathematics relies on. It says, if you have any collection of bins, even infinitely many, you can always select 1 item from each bin. Sounds harmless, right? But mathematicians later proved that if you accept this axiom, and almost everyone does, because so much math breaks without it, you are forced to also accept Banach-Tarski. It's not a separate weird idea. It falls directly out of the rules we already use to do calculus, probability, and analysis. This is why the paradox haunted mathematicians. It wasn't a mistake, it was a consequence of trusting their own foundations. Here's the real lesson. Banach-Tarski reveals that infinity isn't a really big number. It behaves by completely different rules. In the finite world, the world of apples, pizzas, and physical balls, volume is conserved because every piece you cut has a measurable size, and sizes add up predictably. But the pieces in Banach-Tarski aren't measurable at all. They sidestep the entire concept of size. You can't assign them a volume any more than you can assign a color to the number 7. That's why this paradox can't happen with an actual orange or an actual bowling ball. Physical matter is made of a finite number of atoms. You can't divide it into infinitely scattered, immeasurable point clouds. Banach-Tarski lives entirely inside the idealized world of pure mathematics, where a sphere is an infinite continuous set of points. It's not a flaw in reality, it's a flaw, or maybe a feature, in how we define infinite sets. So no, you can't actually duplicate a ball in your kitchen. But the fact that this is mathematically true at all should unsettle you a little, in a good way. It means our intuitions, built from a lifetime of cutting pizzas and pouring water, simply don't apply once you step into the infinite. And the only reason we know that is because 2 mathematicians followed the logic of their own axioms all the way to a conclusion that seemed impossible, and refused to look away from it. That's the strange, beautiful thing about math. Sometimes the deepest truths aren't found by trusting your intuition. They're found by trusting the logic, even when it leads somewhere your intuition says is impossible. If this kind of, wait, that can't be true math is your thing, subscribe, because next week I'm break.